In example 2, we're given that the load P is equal to 4,000 pounds. Here we have a truss with 13 members and 8 joints, and the force supported by member DE is specifically requested. Let's make some observations about the problem before choosing a strategy. First, the truss is statically determinate, so a good way to start is to find the reactions at A and H. We'll get to that shortly, but for now, let's assume we know how to do that and we can find those reactions. Then how should we proceed? The issue with member DE is that it's as far removed from the support reactions as possible. We're going to take a look at 2 solution strategies, of which there are actually many. For solution number 1, we'll have an all method of joints strategy. Note that the examination of joint F tells us that FG is a zero force member. Cross-hatching out FG and re-examining the truss tells us that DG is also a zero force member. This also tells us that the load carried by EG is the same as that carried by GH. Solution strategy number 1 is impose moment equilibrium about A on the whole truss to find the vertical reaction at H. Then impose vertical equilibrium on joint H to find the load carried by GH. Since the load carried by EG is the same as that carried by GH, impose horizontal and vertical equilibrium on joint E to find the force carried by member DE. These 3 free body diagrams will comprise solution number 1. A second solution will consist of combining method of sections and method of joints. As with the first solution, we'll begin by imposing moment equilibrium about A on the whole truss to find the vertical reaction at H. Then we'll define a section that cuts through members CE, CD, and BD and captures the right section of the truss. We'll impose moment equilibrium about joint D for this right section to find the force carried by member CE. Finally, we'll impose horizontal and vertical equilibrium on joint E to find the force carried by member DE. We'll now work through the details of each solution here. Our first free body diagram is of the whole truss. As with our previous problems, there's no reason for us to sketch the details internal to the enveloping surface. So we'll just represent the reactions and the external loads. We could write all of the equilibrium equations, that is, 2 force and 1 moment equation, but in this case all we really need is the reaction at joint H. So we'll write a single equilibrium equation, that is moment equilibrium about A. Here the reaction at H exerts a counterclockwise or positive moment about A through a distance of 32 feet, and the two 4-kip loads exert clockwise or negative moments through distances of 8 and 16 feet respectively. Therefore, our moment equation ends up looking like this. We have H times 32 feet minus 4-kip times 16 feet minus 4-kip times 8 feet equals 0. And solving for H, we find right away that H is equal to 3-kip. If we wanted, we could complete this by recognizing that AY would have to be 5-kip and AX will be 0, but this is all we need right here. Now we can proceed to joint H, and we'll draw our free body diagram, making use now of the fact that H is 3-kip. Here is the force carried by member FH, and the force carried by member GH. We might note also that this angle theta here is defined by a 3, 4, 5 triangle, so we're going to know the sines and cosines of that angle without explicitly having to find the angle itself. Vertical equilibrium then tells us that FGH sine theta plus 3-kip is 0. And therefore FGH is minus 5-kip or 5-kip in compression. We could impose horizontal equilibrium as well to find FFH, but we don't need to do that. We can now go directly to joint E, since we've used the fact that the force carried by EG is the same as the force carried by GH. So finally we have, for joint E, a free body diagram that looks like this. Now I'm going to use the fact that we've just found that GH and therefore EG is in compression. So I'm going to represent the force going into E like this. This is our same 3, 4, 5 triangle orientation. I'm showing this compressing the joint or pushing into the joint because the member is in compression. And DE will look like this. And I'm going to take advantage of the fact that I know my other member CE has got to offset the horizontal component of that 5-kip load, so I'm going to draw that in compression as well. So here we have FCE. And again, that's also making a 3, 4, 5 triangle here. Okay, so here we need both horizontal and vertical force equilibrium. Our horizontal equilibrium equation tells us that FCE cosine theta, which is 4/5 FCE, minus 5 kip cosine theta is 0. And so FCE is also in compression by the same amount as FEG. And our vertical equilibrium equation then says that we have FCE sine theta plus 5 kip sine theta minus FDE is 0. And since FCE is 5 kip, what we end up with is that FDE is 6 kip and the way it's been represented here, that's going to be in tension. So that's our first solution using entirely method of joints. Now what about our second solution? The first part of the second solution is the same as the first part of the first solution, and so we're going to end up here again with our force at H being equal to 3 kip. Now we have a free body diagram for the right half of our truss, and that's going to look like this. Although it isn't necessary for us to show the internal features of the section here, I'm going to do this just to help guide my eye here. So we're cutting through this right-hand side, and we have over here FBD, FCD, and FCE. We also have our 4 kip load, which is captured by the enveloping surface of this section, but just the 4 kip load in the middle. We haven't captured the 4 kip load that's at the 3/4 point from right to left. So our free body diagram looks like this. This is joint D here. And we indicated in our discussion that we would take moments about D, and the reason for that is that 2 of our 3 unknown forces have lines of action that go through D. And so taking moments about D will enable us to find FCE very quickly so we can focus our attention on joint E. So here we'll note that I could resolve my force FCE into its components in the vertical and horizontal direction here. This component is FCE cosine theta. This is 4/5 FCE. And that's important because what it tells you is that the vertical component of CE at E also has a line of action that goes through D. So it's really just the horizontal component of FCE that will figure into this calculation. So if we write sum of the moments about D equals 0, we have contributions just from the reaction at H, the 3-kip load through 16 feet, and we have a contribution from this horizontal component of FCE. Both of them are contributing counterclockwise or positive moments as we've drawn them, which means that ultimately FCE is going to turn out to be in compression here. So if we write this equation, we have 3-kip times 16 feet plus 4/5 FCE times 12 feet is 0. And solving for that, we have FCE is minus 5 kip, or 5 kip in compression. Now we go back to joint E, and in this case we know FCE, we know it's in compression. So now I'll draw this as 5 kip in this way. Again, FDE is here, and we have FEG coming in this way. So again, I'm left with just force equilibrium in X and Y, and I'm going to get 5 kip cosine theta minus FEG cosine theta is 0, and FEG will also then be 5 kip in compression. And in the vertical direction, we again have 5 kip sine theta plus sine theta FEG minus FDE is 0, and using our 5 kip load for FEG, we again get FDE is equal to 6 kip in tension. So these are two of several possible solution strategies we could use to find the load carried by member DE. Our first solution used just the method of joints. Our second solution combined a method of section with a method of joints. There are many additional permutations that you could use here. A suggestion in problem solving, though, is to begin the way we did up here by constructing a strategy that allows you to get to the member that you're interested in. And drawing these different enveloping surfaces to define free body diagrams is an excellent way to start before we start plugging in any equations.